Everyone. So this week we're going to be talking some more about tracing. And so today, last time we talked about logical tracing, and this lesson I want to start talking about physical tracing and how we actually capture realm event graphs that we can then replay very efficiently without having to redo the mapping stage of the pipeline. So actually, let me jump back to our picture of the pipeline here, right? And so last time we were looking at logical analysis, which memoizes the results of the logical analysis. And today we'll be looking at physical tracing, which will memorize the results of physical analysis and be able to replay that very, very efficiently, so that we don't have to redo all of the physical analysis computations that we've looked at, in other lessons. So today I want to talk a little bit about the main abstractions. There's kind of two parts to tracing. So the first part to tracing is that, effectively you need to have something that's going to be able to record, the physical analysis and be able to remember it, right? So you can, and then the second part is the replay part, right? The part where you check that it's, actually able to be replayed, and then, actually replay the execution of the physical analysis. Before we get into details, there's an important detail or difference here between tracing for logical tracing versus tracing for physical tracing, and that is effectively logical tracing. We kind of get a promise from the user that that when they put a begin trace and end trace call right inside of a program, right, we know that the application is always going to launch the same order of tasks and operations and stuff inside of that application. Right, and with the same region requirements and fields and other stuff, and that way, we know that we're able to safely replay the logical analysis. Like all the inputs from the user side are invariant, across replays of the trace. But physical analysis, capturing and replaying physical analysis is a little more complicated, right? Because effectively, there's another source of inputs that we can't necessarily guarantee are going to be the same across trace replays, right? And that is, the mapping decisions that get made both inside the trace as well as outside the trace, right? So, for example, if the user had changed the mapping decisions outside the trace, the input instances, that contain the valid data at the beginning of the trace replay might not be the same as when the trace was captured, right? And so you might not be able to replay, something that you had captured for the physical analysis before, even though you can safely replay the logical analysis every time, right? The physical analysis, there's effectively going to be some preconditions on replaying the physical analysis. And so we're going to see that show up in some of the abstractions here today. And that all stems from the fact that, even though we require users to have this invariant, that all their tasks and region requirements and stuff are the same for traces, we don't require that, they've made the same mapping decisions both before and inside the trace. And therefore, we're going to have these different copies of the capturing of the physical analysis for the same trace, and we'll see that show. Okay, so let's actually go look at some of the data structures here. And the other thing I'm going to say is that a lot of the tracing code is a bit messy, and not everything in here is as clean as it should be. A lot of this code is subject to change in the future. Because tracing has sort of been an evolving feature in Legion, right? It started off as just logical tracing, and then we added physical tracing, and physical tracing has undergone a bunch of changes to adapt to control application stuff, and so some of this code is a bit of a mess and probably not as clean as it should be. And so I think some of the abstractions are good, but maybe the code and the architecture is not quite as good as it really should be. So take all this with a grain of salt and realize that some of this code will probably be subject to change in the nearest future. Okay, so first off, we looked at this logical trace class last time, right? This is effectively what captures the logical tracing, right? And effectively, every parent task context has, for every trace ID, exactly one logical trace associated with it. You'll also notice as a member variable of this logical trace, there is this member variable that is a pointer to a physical trace. Now, not all logical traces have physical traces, so the application can actually say when they put the begin and end trace calls into the application, they can say if they only want to do logical tracing or whether they're going to allow physical tracing or not. And so if they don't allow physical tracing, well then this will just be a null pointer, and there's no pointer to a physical trace associated with a given logical trace. But if they do allow physical tracing, right, then there'll probably be a pointer to one of these physical trace objects that effectively is the same data structure, but just for doing the physical part of the tracing for the mapping stage of the pipeline. And so we can actually look for the physical trace class here. This is all in Legion trace.h. This physical trace class is what's going to restore all of the state needed for representing, a physical trace that we're going to be capturing as part of executing a trace. There's a bunch of data structures in here, but really there's one really important one, and that is this one right here. This is the vector of templates. And so let me introduce to you what the concept of a template is, and then we'll talk about why there's several of them here and what the current template is and stuff like that. So the concept of a template is effectively, remember that I told you that, just because, the user has promised that region requirements and stuff are the same, the mapping decisions might be different, right? And so a template is a capture of a physical trace, with an associated set of preconditions for being able to replay that trace. And, because mapping decisions can change and they might vary throughout the execution of the program, even across, executions of the same trace, we capture multiple different, recordings of the physical analysis, associated with each of those preconditions that might have occurred, right? And so each one of those recordings that we perform will be a different physical template. So template is, a particular recording of a trace with an associated set of preconditions. And we'll look at what some of those preconditions are. We'll talk about them in a little more detail later today. But effectively, you can have multiple different templates for the same physical trace. And in particular, there's often one that has been is either currently being replayed or was the previous replay that was done of this trace, in the prior execution. That'll be the current template, the most recently, executed or replayed one. But there are others that we keep around. Now today we actually, I think, set a bound on how many of these we keep around at a time. I think it's just 5 or 10 or something like that, to avoid accumulating too much memory associated with capturing traces. But you could play around with that bound, and technically, I think in earlier versions of Runtime, it can grow arbitrarily large. And we found that bounding it is actually good because sometimes these templates are actually somewhat memory intensive. And so we try not to capture too many of them at the same time, right, and keep too many of them around. You kind of just need to keep around the most recently replayed ones. And if you throw them away, it doesn't really break anything because, effectively, if you come back around and you threw away one of the templates that you had before, you can just recapture it again, right? It's not going to hurt your correctness at all. It's just a little bit more overhead. You can do another capture and then more replays where you could have replayed it again. So certainly there's some interesting work that could be done to try to figure out how to size this a little bit more intelligently, the number of templates that we keep around. But in general, just keep in mind that there's one physical trace object for every logical trace object, corresponding to every trace ID that the application uses. But there may be multiple templates, capturing and replay, or multiple captures of that same trace in the physical analysis that correspond to different preconditions, and as a result, different, realm operations that we're going to have to execute. Okay, we'll get into some more of these a little bit later. Oh, by the way, there is a pointer back to your logical trace if you ever need that. There are some places where we use that. A lot of these other members we'll get into probably maybe not today, but really the one to just keep in mind is this vector of templates, which are the list of captures that we've done. Let's actually go look at that physical template class here. Okay, so this template class is effectively the thing that stores a trace capture, the results of the physical analysis that get done. And let's actually take a look at some of the member variables and actually talk about what it's actually storing. There's a bunch of methods on this class for a number of different reasons. But the fundamental, trace or template, right? The fundamental part of this template is this data structure right here. This is the vector of quote unquote instructions, needed to replay this template. And you can think of these instructions as a program. This is almost like a very, very simple intermediate representation. It's literally just a list of things to do to replay this template. And these things that you will do, these instructions, quote unquote, are going to be, issuing realm operations, for actually doing particular computations at the realm level for replaying different things, right? And so this vector of instructions, let's actually take a look at this instruction class. It's actually an abstract base class. So look for the instruction class here. Here you go. This is our abstract base class for an instruction. Has a couple of base virtual methods that you need to implement. Really just two. There's the execute method and the toString method, right? This is for printing out traces for logging and stuff like that. And this is the one for actually executing this particular instruction when you go to replay the trace. But then you can see there's like a whole bunch of derived subtypes for this particular instruction. In fact, you can see an enum of them up here as well. But there's whole different kinds of instructions for doing lots of different things. Just to highlight a few to give you some feeling of like what these are doing. Like here's the triggering a user event, from some other event. Here's a merging of event preconditions together. We've got issuings of copies and fills and copy across operations. There's some barrier arrivals and advances down here. Right, and so effectively, these instructions, for the most part, correspond, with a few exceptions, correspond to performing realm operations, right? And in fact, if you actually look at some of these instructions, you can actually see some down here. I'm going to skip this get term event. Let's look at one that's maybe a little more familiar. Like here's a trigger event. Actually, let's do the merge event one. It's probably the most familiar, right? So effectively, like we've written down the operational semantics for these instructions here in the comments, and effectively, well, actually, let me introduce one more thing, and then we'll talk about these operational semantics. You see that these operational semantics are referring to this events data structure that actually exists in this physical template. Let's go back and look at that physical template class again. So we've got this vector of instructions that are actually this physical, the program for this particular template, and they mutate this vector of application events. This vector of application events are effectively like as you're replaying this trace, these instructions will populate this vector and then read from it as well. So like the first event in this vector is pretty much always the fence precondition, which is like the an execution fence event that corresponds to capturing all the stuff before the trace begins executing, and instructions will, read from prior events in this vector, and then scribble, the output events from their instructions back into this vector so that later instructions can read them, right? And so, like, literally just by iterating over the instructions in this program and mutating this events data structure, you can actually, replay the particular trace that you're trying to, or template that you're trying to execute, right? And so effectively, and every time you replay this vector gets repopulated, right? So effectively, like every replay of this particular template will refill in this vector with new events. And what you'll see is that these instructions, they don't actually record events. What they record are indexes into this vector of events, such that they can read to and write from it. So let's actually go back and look at that merge event class here again. Right, and you can see we've written down the operational semantics for this particular instruction, right? Like effectively it takes in all the events in in the set of RHS indices, right? And these are unsigned integers that index into that events data structure. So for you iterate over all the RHS elements here, you read each of those indexes out of this events data structure, you merge all those together, right? And then you scribble your output event, into the LHS index in this events data structure, right? And that's an instruction, right? Like effectively it's doing a realm operation, right, to merge some events together and then produce a new merged event, right, that will then be the process be the output of the particular realm operation and stored back in the vector, right? And that's effectively a program, right? Like you can chain together a whole bunch of these. Like if we look at like issue copy or I guess here's issue fill, here's issue copy. Right, and so issue copy is, something that will issue a realm copy, right? It has some source and destination fields. Again, you've got a precondition index, right? You got some predicate guard, reduction operations, right? These are all, most of this is stored here in the data structure, except for the indices, which you use to, like the precondition index that you use to look up, the event precondition out of that events data structure, and then you write back into this LHS data structure here. All these other members are all stored as like, things that you are recorded here in this instruction. So it's all, recorded as state, for actually being able to replay this copy, right? And so, using this, you can actually replay, pretty much all of a Legion program associated with the physical analysis, right? Pretty much all the realm operations, that you need to do to actually re-execute this particular trace get recorded in this vector of instructions. Okay. let's go back and look at that template class a little bit more, because there's another important part to it. Physical template. So that's, if that's the replaying part, how do you know that it's safe to actually do the replay, right, of this particular program? There's another data structure on here that is also important, and that is this conditions vector. This is effectively the preconditions for this particular physical template. And what do I mean by preconditions, right? So the preconditions are the things that, you know, have to be true in order to be able to replay this particular trace, right? Like these, for example, these instructions, like those copies and fills, are going to assume that the input data to this template, right, exists in a certain physical instances in memory, right? So like, you know, some of the first copy in this set of instructions will assume that there's some input data potentially, right, in a particular instance, and it's going to need to be able to copy from that. If the data for a logical region for this particular physical template actually exists in some different instance, well, then this template is actually not valid, right? Because the template has actually recorded the names of the physical instances of where the data actually lives, right? And so if the data is not actually there, you can't actually replay this physical template. You need to ensure that, you know, certain preconditions are met, like the data for certain logical regions and fields and stuff exist in certain physical instances, such that it's safe to be able to reuse and replay this template and actually execute, you know, a set of instructions that produce a realm of graph that are actually going to do the right thing, right? And this vector of trace conditions are what actually are going to store the names of the preconditions for knowing that it's safe to actually be able to replay this particular template. So let's actually go look at this trace condition set, and, you know, we'll actually see that we'll see why it's actually a vector and not, you know, not just a single trace condition set. So let's actually take a look at that trace condition set here, data structure. This inherits from a whole bunch of different things, but mostly they're very simple classes. But really there's sort of three kinds of preconditions for this trace condition set. Well, actually, I'll say there's like two kinds of preconditions and one kind of postcondition. Importantly, you'll notice that every one of these trace condition sets are associated with a different index space expression. Often these index space expressions are, you know, effectively the set expressions of the equivalent sets that were used to capture the trace. And we'll talk about capture a little bit later. They're kind of arbitrary, right? And, you know, you could try to like unify them all together to create giant expressions. We don't currently do that today because it's pretty expensive. So effectively, you know, you'll have one trace condition set recorded from each of the equivalent sets, you know, that existed, you know, when the trace capture was done in the first place. And each one of those will have its own, you know, condition expression, and then a set of these precondition views, anti-condition views, and post-condition views. So let's talk a little bit about what these various different precondition things look like. Right, you can see there's a trace view set. We're going to go look at this in just a moment. So we'll take a little bit more detailed look at that in just a second. But let's talk about what each of these three different things mean. So these precondition views, these are the views onto instances, like physical instances, that have to exist with valid data in order for this trace to actually be safely replayed, right? And so what that means is that for every physical instance listed in this trace view set, and for every expression and field and so forth, you're going to have to be able to find valid data in those instances in order to or those instances have to be valid copies of the logical regions associated with this index space expression, right? To ensure that, you know, this trace can be safely replayed. So that's the precondition views. The anti-condition views are instances which must not have valid data. They must not be valid copies because effectively this trace is going to actually end up overwriting them, right? Now, in practice, these anti-condition views are almost always reduction instances today, because effectively what that's saying is that the trace is going to, you know, really it's going to want to fill and then perform reductions into that reduction instance. And if you fill a reduction instance that already has reduction values in it that you're ultimately going to need, that can be problematic. And so these anti-condition views effectively are another kind of precondition that effectively is saying like it must not have valid data, right? It must not be part of like the current state of the equivalent set in order to be able to safely replay this particular trace, right? And finally, there's the post-condition views. And the post-condition views are effectively saying, after this trace is being replayed, or has been replayed, these are the currently valid, instances that contain valid data, and what expressions and fields and so forth are, contain that valid data, right? And so, like that's effectively, the way that we actually record that that we've got some post conditions. Let's actually go look at this trace view set, and then you're actually gonna see that we actually do a transpose of these views here into these precondition, anti-conditions, and post-condition data structures. You can actually see these. Actually, I should actually clarify. These are actually probably the real pre and post conditions. And you can see, the data structure is the type def for these expert views here, right? So what you can see is, it's a mapping for, for particular expressions, right? You've got a field mask set of logical views. So these are views onto data, right? And for particular fields that are valid or not valid for these particular expressions, right? In the case of preconditions, they better be valid. In the case of anti-conditions, they better not be, right? In the post-conditions case, it's the what is true after the traces has been replayed. You'll see that the trace view set is actually a transpose of this, where effectively the logical view pointer will actually be here, and the index-based expression will be over or inside the field mask. So we can actually let's go take a look at that. It's the difference between capturing and replaying. This is a trace view data structure here. Has a couple different methods on it, but really you can see, effectively it uses a view expers instead of an expr views. And these view expers are conditions, right? And effectively it's just, like I said, the logical view and the index-based expression pointers are transposed in their location in the data structure. Just a difference between how you record it and how you capture it and test it and stuff like that. So anyway, that's a trace view data structure. This trace view data structure gets used by the equivalent sets as part of their trace capture, right? And then when we actually finish the capture, then we'll do the transpose, over into the representation over here in the trace condition set for actually being able to do the testing for the replays and stuff like that, right? Here's the transposed version of each of these different things, right? And so these trace condition sets record all that information, right? And they're associated with a particular condition, precondition, a particular index-based expression. So popping back up to the physical template here. Let's see here, back down to member variables down here. Right, so you've got a set of trace conditions, right, associated with each of these things, right? And that's how you're able to test for whether this template can be safely replayed or not. So before I go on and actually show you some of the code for where actually some of this testing actually gets done, are there questions I can answer about sort of the structure of these physical templates? There's all sorts of data structures on here that I haven't covered, obviously, but really I've tried to show you the two bigger ones that are the most important for understanding the semantics of how this template works without talking about optimizations and stuff like that.
How does this change with control replication?
Yeah, so that's a good question. There is a derived type of this physical template class. There's actually the sharded physical template class. So this is, you see, it inherits from the physical template. And effectively, this is the version that occurs inside of control replicated contexts. So there's no special physical trace object for control application, but there is a special sharded physical template. And it overloads a bunch of the recording operations for actually recording all of these instructions. I guess I haven't shown you that. It has some additional data structures in here for doing, well, actually, let me say, before I get into some of the data structures, the idea behind physical tracing with control application is that each shard in a control replicated context will record its own template. And like effectively the templates themselves are sharded. So each shard will be recording a subset of the realm graph, right, that needs to be replayed, to replay a trace or to replay a template in a control replicated context. there's no one shard that has all of the instructions, in its template for replaying the whole graph entirely. The different shards cooperate to be able to replay the template together. And importantly, we actually make it so they can do this with zero communication. And the idea is that, there's some special logic when you do the recording of a template in a control replicated context, that if you have an event dependence that's going to span multiple shards, like at least two shards, we actually create barriers, realm barriers, that actually name those events. You can actually see, let's see, we actually don't want the frontiers, we want the local and remote. Let's see, I'm paging all this back in. I wasn't prepared to talk about this today, but let's see if I can actually remember how this works. So these are the frontiers, which are not quite what I want. Let's see. Trying to remind myself. I wonder if I have this on.
We can defer for later.
Yeah. So let me at least give you the flavor of it. Effectively, we create realm barriers that actually span. The realm events that need to go across templates from two different or templates from two different shards, right? So like if one template on one shard is going to produce an event, right, that another shard on a different another template on a different shard is going to need to consume as part of its replay, they each will have the same realm barrier name that they'll use to fill in the events data, the events vector, right, for that particular event. And what you can do then is that realm barriers are really nice. They effectively give you the same name, and you can have lots of generations for that same name barrier, right? And so multiple trace replays can reuse that barrier over and over again without needing to talk to each other, right? One shard will arrive on the barrier, and another shard will use that barrier as a precondition for something else, right? And effectively, that way, when you replay a template in a control replicated context, the shards can replay their sharded template without ever needing to talk to any of the shards or talk to any of the other shards as part of that replay. So they can effectively replay asynchronously with respect to each other and construct a realm event graph that that can be replayed without any communication. And so that's a really nice property of control replicated physical tracing. Now, it does create a little bit of I should also say, you actually see some comments down here in this physical template class about some of these data structures being sharded. Where did it go? Let's see, where were my conditions? Let's see, where did the conditions data structure go? Here it is. You can actually see some comments like this one, right? So like these are the regions that were actually traced. Some of these are sharded for control application, right? And so what that means is that each sharded physical template, right, will have a different set of regions that they're recording. And this is actually important. There's actually sort of like a heuristic that decides which shard is responsible for recording the instructions for various different, regions and fields and stuff like that. And that way you don't get duplicate recording of a particular instruction or parts of instructions and stuff like that. So and I should say, like, this vector of conditions is also sharded, right? So each sharded physical template will record a subset of the conditions associated with the replay. They will each shard will be able to check its preconditions for replaying the template, right? And then they effectively do an all reduce between them to see if they all agree that all the preconditions have been met, to see if it's safe, a Boolean all reduce, to see if they all agreed that it's safe to replay the template. We haven't actually looked at the template, the condition checking code yet, but effectively, conceptually, that's what's going to happen. Like, effectively, they'll each check their conditions and then all reduce between them to see if they all agree that the conditions have been met to replay this particular template. Did that answer your question well enough for the moment?
Yeah, I think so.
Yeah. Effectively, no one shard has all of the instructions for replaying a trace or replaying a template, because some of the templates would be way too huge, right? Like, the number of instructions in these templates is often the size of all the tasks in the program for that trace, right? And so you don't want any one shard to be responsible for doing everything.
Yep, makes sense.
Yep.
I have another more higher level question,
Sure.
but I'll yield to other people if there's anything else.
All right, go ahead and ask him, and also I don't think.
Sounds like no. Okay.
Yeah.
I was gonna ask, would it be possible to be parametric on the instance names for the preconditions?
I think so. Well, this is actually one thing. So I've thought a little bit about this. It's so one thing that I've been kind of dissatisfied with tracing this current tracing implementation is that when you capture a template like this, it actually locks down those physical instances. It assigns valid references to all the instances that prevents them from being garbage collected forever, right? As long as the template is alive. Um, I've sort of thought about two versions of capturing traces that are, one is parametric, right, and the other is at least like allowing it not pinning those instances and keeping them from being collected. I actually think it should be possible for so let's see. Let me give you two answers to this question. The first possibility is that one is we could make it so that traces don't hold valid references to their instances. Instead, they would hold just references that would keep the instance name alive, but still allow those instances to be collected. And before you replayed the trace, or sorry, before you replayed the template, you'd have to like reacquire the instances, right, and confirm they hadn't been collected, and then that would be part of like the precondition testing, right? That you effectively say like, if I can't acquire those instances, if the garbage collector ate them, then the trace should be invalidated, or sorry, the template should be invalidated and deleted, right? The second one that you mentioned is an even more ambitious goal, which is effectively to make these templates parametric in the instance names. And I'm a little. The reason I haven't thought so hard about that one is I'm actually a little bit skeptical that like that we'd actually have parametric traces like that. Like I think that if the instance names change, it's likely that the pattern of copies and event dependencies and stuff, in the realm of event graph would also change as well. Now, I don't have any data to back that up. I'm purely speculating. Like it'd be interesting for someone to do like a study of like, multiple trace captures from the same program and say like, ooh, here's lots of examples where like the shape of the trace, right? The realm operations were all the same, and the event dependent, like the topology of the realm event graph that gets constructed is the same, but just the instance names changed, right? And if you had that, that would be some evidence for wanting to do parametric instances, right? In which case, like then you could, effectively, it really would be like this. The name of the template, for this would actually like be much more meaningful because it really would be like a template that you're instantiating with like different instance names and stuff like that, and then replaying, right? And so that would be interesting. I haven't seen any evidence yet, and I don't have an intuition. I mean, I guess I have an intuition, but I'm kind of skeptical that like there will be lots of traces that are lots of templates that are the same topologically, but don't necessarily use the same instance names. So yeah, that's all.
We haven't even, I mean, in Liquid, as you know, there's an even worse situation where even field names are shuffled between
Right.
essentially identical pieces of the code. So
Yeah, so maybe that's a good example of like why the instance names might change is like, but that would actually require like a change to the tracing code itself because like today the logical traces which are like in order to put the begin and trace end calls into Legion today, you kind of have to promise that the region requirement names are the same and things like that because definitely the logical analysis is not parameterized on field names and region names and stuff like that. I mean, I suppose you could parameterize both of them. That would be an interesting takeaway to see if like you're gonna start seeing traces like with different names and stuff, and just be able to fill in the patterns of region requirements and field indexes and stuff like that. Yeah, yeah. So parameterizing tracing would be an interesting topic. It's not one I've really thought a whole lot about.
Yeah. I mean, other people on this call will know more about this, but I mean, in Liquid, eventually someone will have to trace at some level, right?
Yep.
So either Liquid traces at the level of Python instructions or something, and then gives you a baked trace, or
Yep.
You push that down. But
That's
someone
right.
will have to do it, right?
Yes, someone's gonna have to figure out how to do that or parameterize the Legion tracing or something. Yes. Yep. I'll say that I'll advertise that Rowan and I are having such discussions at the moment. If other folks have input on them, we'd be happy to hear from you. So, yep. Um, yes, that's a good question about parameterization, and certainly you can actually see some of the effects of that non-parameterization here. Like, there's actually names of instances and stuff that are actually used by various instructions and stuff that prevent, the parameterization today. So that's what some of these maps are here. So yes, you can see things like that. Okay. Any questions about that? Or any more questions before I move on to talking about how we test preconditions? And we'll definitely look at testing preconditions today, and maybe we will look at capturing a little bit, and then I think optimization will probably have to wait for another day. Okay, no questions. So let's actually look at how some of this testing actually gets done today. And this is one part that I think is definitely going to need to change in the future, but we'll take a look at how it exists today, and see what it looks like. So we looked a little bit. Actually, let's come back over here to the header file before I dive into some code. So the last time we looked at some of the logical tracing, or sorry, the operations that get injected by the context. If you're doing a trace, we looked at like trace begin up and trace capture up and stuff like that. There's also some operations that only get inserted for physical tracing. And actually, let me actually show you where that occurs. We saw it last week, but I just want to make this very concrete here. So if we look at like begin trace, right? Right, so we always issue like a trace begin up, right? But if we're also doing physical tracing, we also issue one of these trace replay ops, right? Effectively, if we're doing a physical trace replay, that gets stuck into the pipeline as well, right? And then also in the end trace stuff down here, right? I guess this isn't different depending on whether you're doing physical. It's always either a trace complete out or a trace capture up, depending on whether your trace is fixed or not. But one thing I would like to get rid of at some point is this needing a special operation in the issuing part. Ooh, that's the control applicated version, but it's almost the same. But let's just stick to something simple here. Right, this need to issue a special kind of operation for replaying a physical trace, this trace replay op. I would like to get to a place where we can actually avoid that and just make that part of the trace begin op. But well, that's a subject for another day. For today, we've got these special trace replay ops that get inserted if you're doing a physical trace that could potentially be replayed. We issue one of these trace replay ops into the pipeline, right? And so there's trace replay op is another kind of trace op, which is another kind of fencing op. And what this trace replay op is going to do is effectively it's going to test the preconditions for being able to replay a physical template, right? And or sorry, a physical trace. It'll figure out if there are any templates that we can replay, and if not, start capturing a new one, right? So effectively, it'll set the state for the physical trace. Now, let's see. Here's where things get a little bit interesting about trace replay ops. You might expect, coming back to this pipeline over here, you might expect that like the decision about when to replay a physical trace and stuff would actually take place in the mapping analysis stage of the pipeline. And that is really how it should work, but that's not actually where this decision gets made. It actually gets made, as part of this logical dependence analysis here. And you can actually see that, in this trace replay op, because the stage of the pipeline that it's overloaded is the trigger dependence analysis stage, which is the logical stage of the pipeline. Now, this is, I sort of mentioned that this is an artifact of, how tracing used to work and how logical tracing used to work. Logical tracing used to be much, much more expensive. And, when we first implemented physical tracing, the cost of replaying the logical analysis was much, much too expensive. In fact, it would start to dominate even compared to the execution of the physical traces themselves. And so we decided to pull this, this check up into the logical analysis stage of the pipeline and do it eagerly before even replaying the logical analysis stage of the pipeline with the logical trace, because we want to elide even the logical mapping dependence replay and stuff like that. And really avoid as much latency as we could. In retrospect, that was a mistake. This has caused unknown, but very large numbers of bugs and maintenance issues and stuff, because effectively what you're doing now is like coupling together these two stages of the pipeline, right? Like effectively, you need to wait for all the mapping analysis stuff to happen for stuff before the trace, and only then can you run the logical analysis stage of the pipeline for this trace replay op. And that coupling causes all sorts of headaches, and thinking about races and stuff like that, where you've got something in a earlier stage of the pipeline depending on something in a later stage of the pipeline from earlier operations that were executed. It just causes all sorts of headache. And so this is something that will get fixed. But for the moment, when you look at trace replay up and you see that, that trace replay up, does its analysis inside of trigger dependence analysis, which is the logical analysis stage of the pipeline, and that's not what you expect. Just realize there was a reason for this, but it really no longer exists, and this code is going to get refactored and changed to not have to do that the replay in the logical analysis stage of the pipeline. So let's actually go look at this method here, because this is actually where the testing gets done for the preconditions and stuff. Let's see. We're going to go into Legion trace. So here's trace replay out, and trigger dependence analysis is down here. Okay, so here we're in the trace replay out. And it's it's very strange because we're in the logical analysis stage of the pipeline, but we're going to do some physical analysis stuff during this stage of the pipeline. Let's actually take a look at some of this logic here. So there's kind of like there's a couple of different paths here that are actually occurring, right? And there's several I should say, let me try and describe three different scenarios that might occur here. Then we'll look at how the code actually embodies those. So the first case, that you get a trace replay out is that, the physical trace doesn't actually have any templates for this particular physical trace. Like you haven't recorded it before at all, right? And therefore you're just gonna, end up doing the recording no matter what, right? So in that case, that's a really simple case. You'll always end up doing the recording, right? And things are simple. The second case that can occur is that you've got a bunch of templates that you've recorded before, right? And you're going to test, but you're not replaying, no trace has been replayed before this, no template has been replayed recently, and you're just going to go through and, check to see if any of your templates have all their preconditions met. If any of them are met, you'll take one of them and use it to replay, right? And that's the second condition. And then there's a third and special condition, which is an important optimization that we often do for physical tracing, which is if you actually replay, the same trace back to back, which often happens, in big applications which go around loops, right? And that template is what's called idempotent, and we'll talk about what that means. Then you can actually do a much more efficient replay of that same template without even checking the preconditions. So an idempotent template is one that effectively says that the preconditions for that template are met by the post conditions for that template, right? And what that ensures is that you can actually replay those. If you replay those traces back to back with each other, using that same template, you don't need to check the preconditions because the first one is guaranteed to have produced output, that is the same as the input for the for the next one, right? And therefore you can do this very, very efficiently. And so we'll see idempotent templates come up more, but when you see this physical trace have a current template, that's effectively the previous template that was replayed for this physical trace, right? And effectively, if you've got one of those, you're going to be able to do an idempotent replay without even needing to check the preconditions, right? So effectively, there's a couple conditions here, right, to check to see if we need to do a trace capture, right? So if we don't have a current template, right, we're clearly not going to be able to do we may still need to do we may still need to check to see if there's a current template, right, we don't want to do this because, we don't want to do a check to see if we can find a physical template, right? Because, actually, hang on. I am paging this stuff back in for myself. Apparently I've forgotten how this works. Let's see. Oh, okay. So, all right. I'm remembering how this works now. This is the blob of code that I really dislike that effectively traces or checks to see, whether it's safe to do the logical analysis stage, like whether the physical analysis part of the pipeline from prior operations is done before we can move on, right? And you can actually see that here. Oh, I don't know why my screen has locked up. There we go. Effectively, what this little blob of code is doing the coupling between the logical and physical analysis stage of the pipelines. It's waiting for all of the operations that came before this trace replay op that's here in the logical dependence analysis stage. It's waiting for all the physical analysis for all prior operations before the trace, to effectively have finished their mapping stage of the pipeline such that we can now run the logical dependence analysis stage of the pipeline. And we can actually skip this under some very specific scenarios, like if we're going to be recording, right, we can immediately skip, like if there's no prior templates and we're guaranteed to be recording this trace, right, then we can skip this step because like we're just going to record mapping dependencies and move on and run all this. We're not going to replay the template anyway, or sorry, replay the trace, so that's easy. We can skip that, right? And similarly, like if you don't have a current template, you're also going to have to do this coupling, right? So what? Actually, I think I messed up the polarity here on is recording. Pretty much in either of these cases, you have to do this wait and do this coupling to do this testing, and stuff like that. And so these are the cases where we're going to have to do this coupling to actually do some analysis. The one case where you get to skip this is in the case where you've got a current template and you're not recording, right? And effectively you're going to replay the same current template back to back. That means that you've got that idempotent trace optimization, and you can skip that wait, and you're just going to be able to go straight through and replay this. You can see that by the fact that I'm messing up this logic myself, like how complicated it is to couple these pipeline stages together. It's really, really hairy to think about. And as a result, like there have been all sorts of bugs that have been made over the years as a result of this. And so we definitely need to fix it. Okay. Let's see. I guess like the next step here is testing for whether or not we are replaying. So let's see here. Need to find if where is the logic that actually tests to see if we can find a current template. Let's see here. So effectively, I guess we have this like have this current template here. I wonder if this logic is actually in begin trace. I'm trying to here we go. Oh, okay, this is the logic that I'm looking for. This check template preconditions. So effectively, this is the case where we're not doing the idempotent trace replay. We've done the coupling. We've waited on this event. When this event triggers, saying that all the prior operations have finished their mapping dependencies, right? Then it's safe to actually do our analysis. So the first thing we do is we check to see if there's a current template. If there's not a current template, we actually want to try to see if we can find a physical trace or find a template that actually has all of its preconditions satisfied at this stage of the pipeline. So we actually go look at this this check template preconditions method here over in I guess it's in the same file here. Let me actually leave this code here. We'll actually open a new tab just to make sure we don't lose our spot there. Check template preconditions. You'll notice this method is on the physical trace class here, right? And what you see is what we're going to do is we're going to iterate over, our vector templates that we've got, right? And we're going to call this, we're going to pull out the physical template associated with them, and we're going to call it the check preconditions method on those templates, right? To see if they're going to be able to have all their preconditions satisfied, right? And if they can, right, we'll effectively, make this the new current template that we're going to be able to replay for this physical trace, right? And we're going to rotate it, right, so that like we effectively move the most recently used template to the back of the template list, right? That's why this iterates backwards. There's kind of like an optimization here, assuming that you're most likely going to replay the templates that were most recently captured, right? You're most likely going to return to them, right? So effectively, if you choose to replay one of these things, then you can rotate that back to the back of the vector there. And then you can return because you set the current template, right? And that effectively becomes the new template that we're going to replay for this physical trace. Let's actually go look at this check preconditions here. Let's see here. Check preconditions. So this is a physical template, right? Checking the preconditions for this physical template. Right, and what is this going to do? It's going to call this for each one of the vectors in that set of conditions that we looked at before, right? It's going to call this test require method. We'll go look at that, right? And effectively, it's going to give us back an event to say, when have we finished testing all of the preconditions? Because that's actually going to involve a physical analysis, which we'll see. Once we've, if we've got any events to wait on, we'll wait for those events to say whether or not, wait for the analysis to be done, right? And then we can ask each of the conditions if they have successfully met their requirements for being valid, and if any of them are not valid, right, then we can pop back out. We do check all of them, even if we result to false, because that'll actually clean up some physical analysis stuff. Let's actually go look at this test require method here. So here's a test require method, and effectively, what can happen here is we've got a set of equivalent sets associated with this trace condition set that it will know to go do physical analyses on, right? To be able to test. Equivalent sets can be like re-refined, and if they do get re-refined, right, this set can actually be invalidated. We haven't actually talked about that code, but effectively, the set of equivalent sets associated with this trace condition, right, may have changed, in which case we may need to recompute them, right? And so that's what this little blob of code here is doing, is effectively if the set of the set of refinements that pick the equivalent sets changed from the point where the trace was captured to the point where it's replaying or testing this condition, right, we'll actually go recompute the set of equivalent sets needed to actually replay this particular trace condition set. The common case is that they haven't changed, so this invalid mask will always be empty. And then what we do is we iterate over each of these expert views and the preconditions, and we're going to do one of these invalid inst analyses. Let me actually show you where this is. It's something that we've actually seen in prior lectures. Not it specifically, but something that it is a kind of. So if you look for this, we're in Legion analysis, invalid inst analysis. You'll see it as a kind of physical analysis. And we've looked at, update analyses and copy across analyses and other kinds of physical analyses, right, that get done on the equivalent sets. This is just a new kind of analysis that runs over the physical analyses, over the equivalent sets to test them for various different things, right? So an invalid instant analysis is checking to see if any of the instances in this, it's going to check to see if any of the instances in our set of preconditions are invalid for any of the index-based expressions or fields that we need them to be valid for, right? And if any of them are invalid, right, then we're not going to be able to use this template for being able to replay it, right? So effectively, this is going to go talk to all those equivalent sets and check that those instances have valid data for all those expressions and fields, and if not, we're going to record that it's not. Right, and similarly, there's another test down here for any anti-conditions that we've got, right? Any instances that we need not to be valid for any expressions or fields, right? And you can see there's an anti-valid inst analysis here that's going to iterate over all those equivalent sets, right? You can see, we're calling analyze. It's the same method that we call in like update analysis and stuff for traversing equivalent sets, right? And we've also got the anti-valid inst analysis here, right? That effectively checks to see that like all these instances are not valid for all of those fields and expressions. And if they're actually valid or, for any field or expressions, then that will be, sort of a disqualifying condition for replaying this particular template. So effectively, this test require method actually goes through and runs all of these physical analyses. Importantly, we record, our precondition analyses and post-condition analyses. Anti-condition analyses, right? And then here's the check require, right? This is why you always call it, is that effectively it goes through and looks at the results of each of these analyses and checks if they're valid, right? It can say whether or not, the conditions are satisfied and then cleans up, the analyses, removes our references once we're done checking that condition, right? So that's why you always call check require for every trace condition set, so you can clean up those data structures, right? And so coming back to let's see, where did it go? Thought we had our test precondition. What do we call it? Oh, I guess I moved it around. Check template preconditions method here. Right. So effectively, we looked at, we looked at check preconditions here, right? On site. For each of these physical templates, right, and tested to see if all of their preconditions have been met, or as well as their anti-conditions, and that allows us to say whether or not we're able to effectively replay this physical template. To preempt Manolis's question, the same thing can happen with control-applicated contexts. The sharded physical template just checks its local conditions, and then there's also going to be an all reduce. That'll actually happen in the replicated trace replay op, which if we actually look at Legion replication, there's a slight, or actually, I should say, let's see, I guess, let's see, I'm trying to remember exactly. Yeah, the all reduce occurs and then the replicated trace replay op that will actually do that all reduce, across checking these preconditions across all the physical templates across all the shards and stuff like that. Okay, I think we're out of time today for talking about more details about how this works. Actually, let me pop back to this code real quick. I guess we'll finish this method and then we'll run out of time. Okay, so effectively, we have this check templates precondition, right? Effectively, this will check to see if we can find a template to replay if we don't already have a current template, right? And if we actually, this may end up setting, the current template at which place, we'll be able to test whether we're replaying as the, whether we're replaying or not is the test of whether we've got a current template, either because we found one or because we were replaying, an idempotent trace that we had from before, right? And so if we're replaying, right, then we're actually going to be able to start initializing the template to actually do the replay, and actually doing that replay. Otherwise, we're going to actually have to go through and record stuff for this particular trace, because like effectively we don't have a template that we're able to replay, right? Like effectively there's no prior recorded one that we're going to be able to run, and then we do, all the normal logical analysis, like update. This is a kind of fence, so it goes through like the logical analysis fencing stage and stuff like that. Let's see. There are some other tests here for whether or not our replay is going to be idempotent or not, and we do some special stuff if it's, I guess, recurrent is the term here for knowing whether we're replaying an idempotent trace or not. And I guess we're gonna have to talk about that in a little more detail later. But effectively, the logic here, in this trace replay op is a bit of a mess at the moment, and it definitely needs to be cleaned up and made a little bit more clear. And I think that'll happen once we move it out of the logical dependence analysis stage of the pipeline. Okay. So I'll open up to questions, but we're at the top of the hour, so otherwise we're going to stop. So anybody have any questions I can answer before we wrap up today and move on to, we'll come back to physical trace replaying and and stuff, and also capturing next week. Okay, no questions. Everybody's hungry for lunch. All right. Well, I will wrap up for today then. We'll come back to trace replay and hopefully do trace capture and optimizations next time. Thanks, everyone.